Yeah. Okay. Great.
Okay, so if you've already done some stuff with induction before, you can try these problems. 1 second. By the way, which screen can people see right now? Is it the mirror still? Okay, you can try these two problems if you already know the basics. And let me know if you've already seen this before. Um, and okay, till then we will do the other stuff. Okay, so induction is basically taken to be an axiom of real numbers. Okay, you want to see buffer? 1 second. Here, they're in the mirror. You can take a screenshot. Let me know if you're done. Okay, so usually induction is taken to be an axiom of the natural numbers, and it has one of three forms. There's the well-ordering principle, the normal principle of induction, and strong induction. So what well-ordering principle is saying is that if you have any set of the natural numbers, my voice is echoing. Is it like that for everyone?
No, I think it's clear.
Okay, I don't know then. Yeah, so it's saying that every set of positive integers has a least element. So for example, if you take the set 1, 2, 9, 11, then the least element is obviously 1. And similarly, for any set of positive integers which is not empty, it will have some least element. What induction is saying is, suppose you have some property. This property can be like basically anything. Like the property could be this number is even, or this property could be this number is greater than 10, or it could be this number is a root of some polynomial. It could be any property. So what this is saying is if P1 holds, and if you have Pn, then Pn plus 1 holds, then the property holds for all natural numbers. So for example, well, so one example which we can take is 2 times 1 is even, 2 times 2 is even, and we will show that if 2 times n is even, then 2 times n plus 1 is even. And so 2 times every integer is even. That's a stupid example, but okay, I can come up with a better example. So another thing could be, well, you define some recurrence relation Tn, which is equal to Tn minus 1 plus n. This is the triangular numbers. So, well, the property could be Tn is equal to n into n plus 1 by 2. So what you're basically doing is giving a closed form for a recurrence relation. And now what your property could be is P of k is that this holds. And now with induction, what you do is you show P of 1 holds. So, okay, wait, you also start with T of 1 equals 1, my bad. And so P of 1 indeed does hold. You can check that 1 into 2 by 2 is equal to 1. So that works. And you show that if P of k holds, then P of k plus 1 also holds. So suppose you have k into k plus 1 by 2, and you add k plus 1, this would be T of k plus 1. right? Um, and now if you do some algebra, you get k into k plus 1 plus 2 into k plus 1. I'm writing out the numerator here, which is equals to k plus 2 into k plus 1. And the denominator is obviously still 2. So you can indeed see that the pattern holds. So we've shown that if that p of 1 holds, and we've shown that if p of k holds, then p of k plus 1 holds. So we've shown that this indeed is the closed form of this recurrence relation. And this is a very basic example of how induction works. Now, what I would like you, and there's a third form of induction, which is strong induction. So basically, instead of just relying on the previous element, you rely on the property holding for everything before. And using that, you show it holds for n plus 1. And if you can show that, then the property will still hold for all natural numbers. And when you take any one of these as an axiom for the natural numbers, you can show the other two. And so they're in some sense equivalent. What I will give you as a problem right now is show that these two are equivalent. So preferably if someone has not seen this before and they would like to try it, please unmute and speak up.
What do you mean by the question like proving them equivalent?
Okay, so suppose you know that the well ordering principle is true, that every non-empty set of positive integers does have a least element, then you need to show the statement of induction holds. So now you have some arbitrary property, you know that p of 1 holds, and you know that if p of n holds, then p of n plus 1 holds. You need to prove this, that p of I holds for all natural numbers I. So would anyone like to try? I can give you 1 minute to think about it. Yes, Saksham?
So, like going by the well ordering principle, since if we take the entire set of positive integers, then we can see that one is the least integer, the
Sure.
least integer is then we are given by the process of induction that P of 1 holds. So the property holds for 1. And we're
Okay.
also given holds for n, then it holds for n plus 1. Now,
Yes.
since there is nothing before 1 by the well ordering principle, so I don't have to worry about that. Now, if P of 1 holds, then the property holds for like n equal 2, then n equal 3, and so on, and it holds for all natural numbers.
Well, no, but induction is that and so on. And what we are trying to do here is to prove induction holds. So you can't really say and so on. Also, just a second, someone would like me to repeat well ordering. So well ordering principle is the statement every non-empty set of positive integers has a least element. So if you take the set of even numbers, that least element would be 2. If you take the set of all odd numbers greater than 6, then that the least element would be 7. So yes, you have
I
to
have
show the
another.
well ordering principle implies induction. You can't
Can
just
we
say
just
and so on.
Oh yeah. Can we just say that, by well ordering principle, first one is the least integer. So if
Okay.
it holds for one, then it holds for two. Now remove one from the set, take two to infinity. Now two is the least integer, works for the next number. So P of three works. Remove two, and this process continues on until whatever we want.
Okay, that's closer, but it's still not entirely correct. So yeah, first we used 1 to show 2 and then you used 2 to show 3, but you said remove 1 and then remove 2. Again, you can't just like do that. Um, because again, that sort of still needs induction. So if anyone else would like to try, or if you have a different idea, then let me know. Else, I'll just tell you the proof. Anyone? Which question we talking about? Okay, you have to prove that the well ordering principle implies the principle of induction. I can give you a hint, which is use proof by contradiction. Try to like form. Okay, I think I'll tell you the proof because otherwise there will not be enough time to do problems. So suppose for contradiction that pi does not hold for all natural numbers, right? So let S equal the set I such that pi does not hold. Does anyone want to like step in now and try to complete the proof, or should I continue? Okay,
We
I'll
have to
continue.
like prove that this
Yeah,
set is
sure.
empty.
Sorry?
We have to like prove that this set is empty. Like,
Yes, you have to prove the set is empty.
okay.
So how do you want to do it? All right. Well, we know the well ordering principle is true. We're trying to prove well ordering implies induction. So the only way we can use it here is S has some least element, call it X, right? Okay. Now, wait, okay, I'll call it M because X does not sound like a natural number. Anyways, so because M is the least integer such that the property does not hold, what we can infer is that P1, P2, and like all those are irrelevant, but in particular, Pm minus 1 holds. Now, what's the second thing we know? We know that if Pn holds, then Pn plus 1 holds. We know Pm minus 1 holds, so we know Pm holds. But, well, we started with the assumption that Pm does not hold because M is in S. So, assuming that S was non-empty, uh, let us choose the least element. And then we showed that least element is not really an element of S, and that's the contradiction. So S must be the empty set. Our set S is empty. So, well, if a set is empty, then this is the set of all the numbers where pi does not hold. And since it's empty, then pi holds for all numbers. Pi holds for all natural numbers. And that is exactly what we wanted to prove. So that finishes the proof. Did anyone not get that? Okay, you want me to repeat it again. So we we suppose for contradiction that pi does not hold for all natural numbers. Then we can take the set of all the natural numbers so that pi does not hold, call the set S. So, and this is non-empty because it does not hold. And now by the well ordering principle, the set S has some least element M. Now, but so we also know that everything before M, pi should hold. So in particular, Pm minus 1 holds. But now, as part of our induction hypothesis, we know that if Pn holds, then Pn plus 1 holds. Now we take n equals to m minus 1. So Pm minus 1 holds, and that gives us Pm holds. But well, we assumed m was in S, i.e. Pm does not hold. So that is the contradiction. That contradiction came from assuming that S was non-empty. So in fact, S must be empty. And so pi holds for all natural numbers. Did everyone get it? Okay. So the proof for we are using induction to prove induction from well ordering. What do you mean by that? No, so induction is the statement that if these two hold, then this holds. That is what induction is. Now we want to show induction holds. So we are allowed to assume that these two hold. And in addition, we know that the well ordering principle is true. So we have to combine this and these two to get this. Yes. Okay, so I guess now would be a good time for some problems. I'll try to start with a easier problem. So suppose you did not know what modular arithmetic is, and if you don't, then you don't need to worry. We will show an interesting, we will show like a problem in number theory using induction. This is the problem. I'll give everyone 2 minutes to think about this. You need to use induction to prove this. Yes, so someone said you can use basic induction. Would you like to say your proof out loud? If you, okay, if P1 holds and Pn holds, Pn plus 1 holds. Okay.
Yeah, I think I got a proof there.
Sorry?
I think I got the answer.
Yeah, please go on.
So, like we can just first use the base case if n equal 1,
N
then
equals 1, then 6 to the 1
the
minus
n
1 is
minus 1
5,
is
and 5
5.
divides 5. Yes.
Yeah. Now we just assume that it's like true for some value k. Now let's if we look at this value 6 raised to the power k minus 1, we can just rewrite this as 6 multiplied by 6 raised to the
Wait,
power k minus
are you going
1.
from k minus 1 to k or k to k plus 1?
No, I'm going from k to k plus 1. I'm assuming it's true for k.
Okay, sure.
Yeah, I'm just restructuring 6 raised to the power k plus 1 minus 1 to get that it's equal to 6 times 6 raised to the power k minus 1 plus 5.
You
And
mean 6 to the power
since,
k? What have I written? Sorry. Uh, yes.
yeah, well, 6 raised to the power k minus 1 comes in a bracket and you can just add plus 5.
Sure. And now by the induction hypothesis, 5 divides this and 5 divides this. So 5 divides the whole thing. So we are done.
Yeah.
Go ahead.
So can you say that like for any part of like 6 part of n is always 1?
Yeah, that's what you would say in, if you are using congruences, but
Yeah,
right now we're assuming you don't know that.
but if I use congruence to prove it. So if 6 part of
Yeah,
1,
by congruences, it's basically trivial. You don't
yeah,
need to say anything.
okay.
Yeah. Okay. That was quite a simple problem. Now, let's try a nicer problem, which some of you might have seen before. It's quite popular, but the proof that you saw for it probably was different from what I will try to show here. So this is the problem. You have 1, 2 till. Okay, someone's saying parity. Yes, I know there's a solution using that, but we will try to show a different solution here. So you have the set of numbers 1 till 2n. Sure, yeah. Yeah, that's correct. Okay, so now you're giving any n plus 1 integers. So you have some set of n plus 1 integers, a1 till an plus 1, and S is a subset of this original set. What you need to show is that there is A and B in S, so that A divides B. There's a proof using pigeonhole principle, which is very nice, but we will try to use induction here. I'll give you 3-4 minutes to think about it. Manan, what do you mean one of them must be at least half of the greatest? Less than half. Right. Okay, how does that help? Okay, I think I'll give some sort of a hint. You won't use induction, so, well, suppose we know it's true for 2n. We know it's true for 2n, so we want to prove it for 2n plus 2. And we have n plus 2 integers. So, okay, well, for 2n plus 2, the problem is almost the same, but instead of till 2n, you have the extra numbers 2n plus 1 and 2n plus 2. So you have 2n, 2n plus 1, and 2n plus 2. And we have n plus 2 numbers. So Suppose you have n plus 1 numbers from this set. If amongst these n plus 2 numbers, you have n plus 1 numbers from this set, then you can use the induction hypothesis and finish. Right? Does anyone see why?
Because we have assumed that it's true for any
Yeah,
or like
exactly.
2n.
So if you have n plus 1 out of these n plus 2 integers, if n plus 1 are from the first 2n, then you're already done. And so we assume that n plus 1 are not from the first 2n. In particular, we will have both of these are in our set. So
उसमें भी रिचार्ज कर दिया पापा जी है ना हाँ हाँ वो क्योंकि उसमें कर दिया इसको गया
you're
मैंने रिचार्ज
unmuted.
हुआ था मैंने बोला जियो का नंबर है 8595 डाला अब मेरे मन में अभी बड़ा
Should, okay. So now we know 2n plus 1 is an S, and we know 2n plus 2 is an S. And the remaining n numbers, remaining n, n are from 1 to 2n. N numbers in 1 to 2n. To 2n. Now, we have n from these, and we have these two. Somehow we need to combine this to get two numbers, which one of which divides the other. Now, 2n plus 1 is not very nice. Like, 2n plus 1 could be a prime number, 2n plus 1 could be anything. We don't have much control over it. But 2n plus 2, this is quite nice. Why? Because it's 2 times n plus 1. And n plus 1 was in our original set. Like n plus 1 lies in here. And we are given 2 times n plus 1. So somehow we need to use the fact that that works out quite nicely and prove the result. I'll give you 2 more minutes to think about how to finish from here. It should be doable by most of you. Just try and think about it. Sure, here's the problem once more. Okay, wait, Zohad, I think you have two accounts in the meeting. So you should like probably remove one of them, or else it'll echo.
I think your voice is echoing quite a lot of times.
I'm sorry?
I think your voice was echoing a lot.
Yeah, I think someone has two accounts in the meeting and they unmuted, so it was echoing. I hope it's not happening now.
Yeah, yeah, sure.
It's patched.
Okay. So Geo is good says we are done. Could you like unmute and speak up? You say we want one extra number in the set. You're right. So how do we get that?
Okay, so we can just choose any other number in the set. Like we can choose 2n plus 1. Then we would have the original set we originally held.
Yeah.
Otherwise, if we had 2n plus 2n, 2n plus 1 in the set, then we can
Yes.
remove one extra number from the set.
You can remove one?
If we like including 2n plus 1 and 2n plus 2 in the set, then we can remove some extra number. And then 2 divides or n plus 1 divides this thing.
2 divides what?
2 divides 2n plus 2.
How do you know 2 is in the set?
No, we had the oh yes.
That's fine, yeah. No worries. You have 2n plus 1. I mean, you have 2 times n plus 1, which is 2n plus 2. In some sense, this is, yes, n is natural numbers. In some sense, this is like very similar to n plus 1. And n plus 1 is nice because n plus 1 belongs to this. What do you mean? Of course, 2 is in the set. Um, we have, no, wait. We have this set, hold on. We have this set from of all the natural numbers from 1 to 2n. We have a subset of this set, say S, and wait, what happened here? Sorry. Yeah, we have a subset of this S, cardinality S equals n plus 1, right? It's a subset of this set. We want to show there's two numbers in S, which one of which divides the other. So we can't say that some particular thing is there. Yeah, if you are talking about the main set, then the problem is trivial, right? There is no problem. So what Geo is good said correctly. If you have n plus 1 integers from the first to n, then you're already done. Because you can just use the induction hypothesis. Remember, we're using induction here. Well, also, side note, you do need to verify the base case, which is 1, 2, and you have two numbers from this, and 1 divides 2, so the base case works. But you should always make sure to check that. Don't try to do induction without knowing the base case is correct. That can lead to bad stuff. Anyways, so we're trying to use induction here. We have the hypothesis for 2n. We need to prove it for 2n plus 2. So if n plus 1 of our n plus 2 integers are from the first to n, then we're already done by the induction hypothesis. The only other case is that n integers are from the first to n, and you have 2n plus 1, and you have 2n plus 2. And n other numbers are from the first to n. Now, 2n plus 1 is not very nice. It could be a prime number because it's odd, like you don't have a good control on its factors. But 2n plus 2 is just 2 times n plus 1. This is quite nice. You need to use it somehow. How are you going to use it? So to clarify, we are working in this case. We have A1, A2 till AN. We have 2n plus 1. And we have 2n plus 2. The AI belongs to 1 to 2n. And you want to find some stuff which divides another number. Okay, Saksham, what is your idea?
No, I just feel like if n numbers are supposed to be taken from those two n ones, then I don't know. The idea that if there are two n numbers, then there are n odd and n even. I don't know if this idea can be put into use here.
Okay, that you can use parity. That actually leads to the other proof by PHP, pigeonhole principle. But what?
Yeah, my proof was like, if all n are odd, then
Yeah.
that must also include like three and stuff. And
Hmm.
by In the small arithmetic, we can say that 2n plus 1 or 2n plus 2 will be divisible by 3, so we are done. If it's all
Yeah,
even, then of course 2 is there. But if there is a mix, then I don't know what's going on.
yeah, exactly. You don't know if they're all odd or all even. That could be a mix. You can't say much about it. So that's the issue. We need to resolve it somehow. Okay, I'll give you another idea. So let's let's just throw this out. We don't even care about 2n plus 1. Like it's in our set, but it's irrelevant. So we will like take this set S prime. S prime is basically the same set, A1, A2 till AN, but we make two important changes. First of all, 2n plus 1 is not nice. Forget about it. Secondly, we will replace 2n plus 2 with n plus 1. Why? You will see why in a moment. So this is our new set, S prime. What do you see about S prime? Can someone tell me something about S prime? Okay. Well, for starters, okay, there is one issue that could arise. That is if any of the AI equals to n plus 1. Suppose some AI equals n plus 1. Then can someone say why this is not an issue? Suppose I'm telling you that you have the original set S, you have 2n plus 2, you have 2n plus 1, and one of the AIs is n plus 1. What happens? Come on, someone. People. If you're already given that one of the AIs is n plus 1, then obviously AI divides 2n plus 2 because n plus 1 divides 2n plus 2. So if you know one of the AIs is n plus 1, then you're done. It divides 2n plus 2. Yeah, exactly. So we will also assume AI is not equal to n plus 1. Now what? So now we have this new set S prime. What do we see? Cardinality of S prime. What is the cardinality?
N plus 1.
N plus 1. What else do you see? Well, all of the AIs are from 1 to 2n. You had 2n plus 1, which you forgot about. We don't care about it. And you had 2n plus 2, but you replaced it with n plus 1. So every element of this set is an element of 1 till 2n. Right? So we have this set. And now again, we can use the induction hypothesis. So there exists some two elements, A comma B in S prime. By the induction hypothesis, A divides B. We know this. There are some two elements in this set. One of them divides the other. This set is very close to our original set, but it's not the same. We need to somehow make it the same. How do you do that? No, like, see, we already had 2 multiplied originally.
Okay.
We divided by 2 to get this nice set. Now we use the induction hypothesis in this set and we found A divides B for two numbers A and B. Inside the set S prime. We are working inside S prime right now.
Okay.
So
So now, do we have to um, show that there exist two numbers also for S?
exactly, yeah. So now you need to use this to show that there is also two numbers in S. So now, like, when is there a problem? So what do I mean by when is there a problem? If A is equal to some AI and B is equal to some AJ, so we know that some AI divides some AJ, then well, there's no issue, right? AI and AJ are also part of S. So you're done. Right? Does everyone see that?
Briefly, like recap the flow of the answer, the solution that we have just found. You have just
Okay, so we have some S. S is a subset of. Okay, wait, no. To start with the starting, we assume that for all for all subsets, for all A, which are a subset of 1 to 2n, and cardinality of A is equal to n plus 1, then there exists AB in A such that A divides B. Also, if at any point you don't know what notation I'm using, feel free to ask. This is a like a backwards E, it means there exists. All right. So now we have some subset S. S is a subset of 1, 2 till 2n plus 2. Cardinality of S is equals to n plus 2. We need to find A and B in S so that A divides B. Now, suppose n plus 1 numbers in S are from 1 to 2n. Then we can just use the induction hypothesis and we're done. So we know that at most n numbers are from 1 to 2n. The only numbers outside of 1 to 2n in S can be 2n plus 1 and 2n plus 2. So we have n numbers from 1 to 2n, we have 2n plus 1, and we have 2n plus 2. So S is equal to, wait, I'll just copy paste this because I've already written it. I don't want to write it again. So, shouldn't have it. Yes. S is of this form. A1, A2 till AN, 2n plus 1 and 2n plus 2. AI belong to 1 till 2n. Now, we see that 2n plus 1 is not so nice, and 2n plus 2 is especially nice. That motivates us to consider this new set S prime. What is S prime? Well, S prime, as I wrote earlier, is, okay, I'll just write it again. A1 till AN and n plus 1. Okay, now we will see that cardinality S prime is equal to n plus 1. Why? There's A1 till AN and then there's n plus 1. So that's n plus 1 elements. Okay, but there might be an issue. What if one of the AIs is equal to n plus 1? Right. Then there's two of the same element in the set, and sets don't count elements twice. Okay, why is that not an issue now? Suppose one of the AIs is n plus 1. Then we go back to our original set S, and then AI divides 2n plus 2. In this case, we are done with the problem. Why? We found A and B. We found this A and B in S. AI divides 2n plus 2. So we are done with that. Now we can assume AI is not equal to n plus 1 for all I. Okay, so then we indeed do have that the cardinality of S prime is n plus 1. What we also have is that S prime is a subset of 1 till 2n. Okay. Now, again, we use an induction hypothesis. A is a subset of 1 to 2n, cardinality A equals n plus 1. Then there exists A and B in A such that A divides B. We can use that in S. So we have A, B in S. I meant S prime, sorry. A and B in S prime such that A divides B. Okay. This is roughly where I got to. Did everyone follow till here? Yes? Okay. Any no's? All right. Okay. Okay. We have A divides B. Now we want to somehow conclude some stuff about S using this. Okay, so what can A and B be? Like what numbers can they be? A is like one of the AIs. It's either some AI or it's n plus 1. Importantly, A is not equal to B. Otherwise, obviously a number divides itself, right? Yeah. So A can be some AI or n plus 1. B can be some AJ or n plus 1. I and j are just like dummy variables here. We don't really care what they are. They're like something between 1 and n. Okay. So now we sort of have three cases, right? Case 1, A is some AI and B is some AJ. Okay, so AI divides AJ. But AI and AJ are already in S. Like S also has AI and AJ. So we found two numbers in S so that one divides the other. So we are done. Okay, that's case 1. Case 2. Well, case 2 is A equals n plus 1. At this point, it's just direct go with PG. Oh, sorry. Go with PHP, you mean? Okay, you can use PHP. Like, I'm not saying that's a bad thing. It's probably a simpler way to do it, but this is a class in induction. And I thought this is quite instructive. Like, doing this with induction gives you some like insights on how you can solve any problem with induction. And like, if you think it's direct, then you can unmute and give me the solution from here. I will write down what you say. Okay, so this is case 2. We know that A divides B. So n plus 1 divides AJ. Well, what are the multiples of n plus 1? We have n plus 1, we have 2n plus 2, and so on. Right? Now, this is the set S prime we are working in, remember. So the only numbers in S prime are between 1 and 2n. So AJ is between 1 and 2n. So 2n plus 2 is not possible. N plus 1 is the only possibility. But again, A is not equal to B. So AJ can't be anything. This is just not possible. Does anyone have an issue with this? Like, do you have any confusion? All right. Case
No.
3. Okay, here. A is equal to some AI and B is equal to n plus 1. So, okay, AI divides n plus 1. Now, does anyone want to finish? Like, come on, this is the last line of the proof. Conclude. Remember, you need to go back to S, the set S. Anyone? Okay, can you explain case one? Okay, case, so what, what do you mean? Okay, yeah. Case one, so A and B are elements in S prime, right? Now, S prime is the set A1 till AN and then N plus 1. So A must be either some AI or N plus 1, B must be some AJ or N plus 1. Case one is when A equals AI, B equals AJ. So we know AI divides AJ. But remember, S also has all these AIs and AJs. So A and B are also elements of S. In this case, AB and S, AB and S, and A divides B. This is exactly what we wanted to show. In case two, we showed, well, N plus 1 can't divide anything here. Like, it doesn't work out. In case three, A is AI and B is N plus 1. AI divides N plus 1. Now we need to go back to S and finish. We need to give some A in S and B in S so that A divides B. Would anyone like to finish the proof? This is the last line.
What do you mean, like, we have to find some A and B in S such that A divides B? We are assuming that A is AI and B is N plus 1. So isn't like B fixed?
Okay. This is in S prime. These are in S prime, right? We use the induction hypothesis on S prime, and we have this. Okay, okay, don't call them A and B. Give C, if like we already used A and B, sorry, so I shouldn't have said that. Give C divides D, give C and D in S so that C divides D. If we are working in case three, what are these C and D? Come on. Remember, we know that some AI divides N plus 1. Anyone?
Wait, if some AI divides N plus 1 and AI is not equal to N plus 1, so we can just like take these two numbers itself.
But this is S prime. We don't know that N plus 1 is in S. Like, remember, we took this set S and we created this nice new set S prime. S prime has cardinality N plus 1. So we can do nice things inside it. We can use the induction hypothesis. But, well, N plus 1 might not be in S. But what is in S? What what number was
Interesting.
especially nice? Okay. Well, AI divides N plus 1, so certainly it divides 2N plus 2, right? Yeah. No, wait, Saksham. Again, you don't know whether 2 is in S. What you do know is that AI divides N plus 1 and AI is in S. But N plus 1 divides 2N, yeah, AI and 2N plus 2. So AI belongs to S. This is in S. n plus 1 may or may not be NES. We don't know. N plus 2 is definitely NES. And AI divides to n plus 2. So we're done. Exactly. Yes. Suction. That is exactly what happened. Yes. That finishes the proof. I'll give you like 30 seconds to think about what just happened. It might be a bit difficult. How AI divided 2n plus 2. Okay, so we were working in S prime, remember. By the induction hypothesis for S prime, there is some A and B, so that A divides B. The numbers in S prime are all some AI, or it's the number n plus 1 itself. In case 1, A equals AI, B equals AJ, and in this case, these numbers are automatically NES. So we're done. In case 2, we showed that it's not possible for n plus 1 to divide AJ. Like this case is just invalid. This is case 3. A equals AI, B equals n plus 1. We know that AI divides n plus 1. So of course it divides 2n plus 2 as well. Like if A divides B and B divides C, then A divides C. Okay, so I've only seen this problem in the context of PHP, so I came up with this proof on my own. There's probably some version of this online somewhere else. Like, it's a very well-known problem, so I'm certainly not the first one to think about it this way. But how do AI divides n plus 1? By the induction hypothesis. You know there's two numbers like that. We used our induction hypothesis, we did some case work, and in this particular case, we know that A divides B, and we know that A equals AI, B equals n plus 1. So, and we know A divides B, so obviously AI divides n plus 1. Okay, I'll give you guys a new problem. By the way, has anyone been working on these two problems, the buffer problems?
Can we just go back to the last question once?
The last question?
Yeah, the question that we just.
Yeah, do you want to see the question or?
No. In case 3,
Yeah.
I just have a question. What if n plus 1 is prime? So,
How does that change stuff?
no, like you say that A divides B,
Yeah.
and if n plus 1 is prime, A has to be n plus 1,
Okay, yeah.
which means that A is equal to B. And
Yes, you're right. You're right. We know that A divides B, and if suppose n plus 1 is prime, then sure, A must be either 1 or n plus 1. It can also be 1, remember.
yeah, it can be 1.
But
so we are not.
if it's 1, then we're happy, right? If it's 1, then we're happy. It works. If it's n plus 1, however, if A equals B, well, but by the induction hypothesis, A is not equal to B. Like, we knew the problem holds for the set 1 till 2n. For any n plus 1 subset of 1 till 2n, we know there's A and B such that A is not equal to B and A divides B. So if n plus 1 is prime, then yeah, you're right that this case does not make sense. But we don't need this case to make sense. That means it's one of these two cases. Like these cases cover all possibilities. So we don't ever reach case 3 in that case. So yeah.
Yeah, got it.
All right, I'll give you the next problem. This has some geometry, so hopefully the geomins will appreciate it. Will you be giving? Sure, I can send that. I have a set of about how many problems is this? 18 problems, so I can send those afterwards. Yes, I will share it after class, don't worry. I'll send it to like one of the OMC people and they'll send it to you. So this is the next problem we're doing. I'll give you 3-4 minutes to think about this and then we can discuss what all ideas you have. I'll not be there for a moment. Okay, someone seems to think this is from Rushel's book. Well, the one in Rushel's book is about equilateral triangles, I think. Is it? Wait, let me check. Yes, so Rushel's book problem is for equilateral triangles. This problem is for non-equilateral triangles, so they are not the same. Any ideas?
How about we like first start by finding a way to do it for n equal 4?
N equals 4. Sure. Okay. We have like some random triangle. You can try for any. Also, for people who have not seen this before, I should clarify. Induction says if P of 1 holds, and if P of n holds, then P of n plus 1 holds. So okay, so wait 1 second. All right. Okay, so yeah, in induction, our base case was 1. That was the only base case specified. Here, our base, where did the problem? Here our base case is k equals 4. So how is that allowed? Well, P of 1 can just be Q of 3 plus 1. So we have like some property holds for. Okay, someone is saying we should take base case 6 as mean tends to 6. Okay, but if the base case is 6, you still need to prove it for 4 and 5 separately. So that doesn't really help. Yeah. Okay. So we want to start with base case 4, right? So induction only allows us to start with base case 1. So how are we starting with base case 4? Well, you can change the property itself. Like you can say this property Pi, which you're working with, is some different property Q of 3 plus I, and that starts at 4. Like, do people see what I'm saying? All right. So we have the base case of n equals 4. We want 4 isosceles triangles, and we have some non-equilateral triangle. What do we do? Take perpendicular? Okay, good idea. That's a good idea. All right. Now we took some perpendicular. Call this ABC because why not? What do you know about right triangles? Yes, midpoints of hypotenuse. So, all right, this length is equal, this length is equal, and this length is equal. This length is equal, this length is equal, and this length is equal. Does everyone see why these lengths are equal? Have you seen this before? Or draw some sides parallel to original side and middle of originals. Wait, like here, and then here and here. I'm not sure if that works. Yeah, like say you have, wait, okay, I'll just you're saying we have this, this, and you want this, x, y. What then? Yeah, but what does this give you?
I think he meant like median triangle.
Median triangle. Okay, AXY is isosceles, but what I mean, you want 4 triangles, and you want it to be a dissection of only triangles. Like this is a trapezium. Okay, same for all. Okay, so you do mean median triangle. Okay, so this, right? Okay, that's 1, 2, 3. Wait, also, wait, no. I mistakenly said AXY is isosceles. Why is AXY isosceles? It's not.
Oh yes, it need not be isosceles.
Exactly. In this case, however, we are done. So this is the midpoint D. Call this like E and call this F. These are the 4 triangles. Well, why need not it be as okay, fine. Let's look at something less symmetric. This figure is too symmetric. Okay. You have something like this. You're saying connect the midpoints. How is this triangle isosceles? AXY is not isosceles, right? But what? No. We have a non-equilateral triangle. Again, the problem in Russell's book is equilateral triangles. This is non-equilateral. So that does not work. All right, but what Ayush said does work. Like this is correct. Okay. So this is valid for n equals 4. You can always do this. But wait, no, can you always do this? What if the triangle itself is a right triangle?
Then you
You can
like
still do
take
it.
the
You just take the non like
yeah.
you take A to be this like right angle side. So you can always do this. All right. How do you want to like yeah, you can do this. You're right, Ayush. No, this is just n equals 4. You need to show this for all n greater than equal to 4. So we're not done yet. So, okay, we have a triangle. Yeah, what if its right triangle altitude will be AB only? Yeah, that's exactly what I was asking you. But well, it, that is only an issue for one orientation. You can just rotate it, right? Like, okay, you're saying this is your right triangle. This is the altitude. This is the altitude. But now you just choose this third altitude. So that's not an issue. In this again, you do like this and this, whatever. So that's not an issue. Okay. So, okay, Ayush, you're saying even n. That's interesting. Why even? Like dropping the perpendiculars was the right idea. Okay, take a perpendicular, sure. Now what? To the smaller triangle? But what do you want to do now?
Like inside the triangles we have already created, like in the above diagram. For
Okay,
example, the triangle
yeah. So you want to use induction. We can put more altitudes. Okay. Um, sure. You can do it in this. But how does that work for all in? Like, sure. You can do it in this and you can do it in this. So what is our induction hypothesis? It's possible for all n less than or equal to k, less than or equal to 4. And we want something for k plus 1. Let's say I dissect it in 5 triangles where 4 are isosceles. No, that does not count. Dissection, like all of the triangles are isosceles. Yeah.
Can we draw more perpendiculars like from for triangles A, C, D, A, F, D, and then use induction? I think you're new.
Yeah. Oh, sorry. You repeat what you did in the big triangle in the smaller triangles. So you want to induct.
Yeah, that's
But like, let's not draw the perpendiculars yet. So, okay, take this ADC. ADC can be split into, say, we can dissect this into anything between and in like, we can again dissect this for some 4 less than equals to n less than equals to k. So, okay. If n is true, n plus 4 is true. Correct. So we take one of these. So this is our original dissection. So this gives us 1, 2, 3, 4. And we take this, and by induction hypothesis, we have n over here. So that indeed does give us n plus 4. So now, if you can show 4, 5, 6, and 7, then you'd be done. Six is done by medians. Do medians? Why do medians work? Wait, okay. We can try. 1 second. They will. Why aren't we drawing parallel? What do you mean by that? Okay, these are our medians. What do we know? We know, yeah, equal areas, but we want isosceles. I mean, you have 6 triangles, sure, but these lengths are, we don't know anything about the lengths, those lengths. So this doesn't give anything. After drawing 4 oh, hello Sanskar. Okay.
Hello.
After dividing into 4 isosceles, we draw parallel sides and get +1 triangle for each time. Okay, so now you're saying this triangle 1 is isosceles. So do this. And this gives 1 more. But what about this? This is now a trapezoid. You need to turn it into triangles.
Can't we just make another perpendicular?
Another perpendicular where?
Yeah, like
Are you saying
or
here, here, and like here? Like how? What? So no
no,
trapezoid? Yes,
because
a dissection. I should have probably specified this before. A dissection into triangles is basically you are cutting up the shape into n triangles. All of the triangles are isosceles. You don't have any other shapes. So it's just these n triangles.
because all of these 4 triangles are isosceles, we can make a perpendicular which divides. Okay, that doesn't make it isosceles.
That doesn't make it isosceles.
Yeah.
Okay, it seems maybe dropping this perpendicular was not the right idea. Right? Okay, it worked here. We were able to turn 1 to 4. We were able to get 4, but maybe it does not work in general. What else can you do? The important assumption is that it's non-equilateral. What does that mean? You have these sides. You have the side of length A. You have the side of length C and B. Why can't we draw more altitudes? Well, no one's stopping you from doing it, but what did you get? Like, were you able to prove anything with that? Dropping altitudes gave n to n plus 4. But we don't want this gap. We want n plus 1, n plus 2, and n plus 3. One way to resolve this is to do the base case of n equals 5, n equals 6, and 7. But do we want more base cases? Like, you can try to do that. I'm not saying it won't work, but there's something better.
So you can go from n to n plus 4, right?
You can go from n to n plus 4. So it will become 5 and 1 more 6, etc. Manan, I'm not sure that's correct. Geo is good. Okay, you think some other algorithm might also work. What is this other algorithm? Extremal principle. I mean, okay, so induction is just in some sense like similar to the extremal principle. They're both using local information. Okay, Shreyas, you have one more idea. What is it?
Actually, that is n to n plus 3 now. Why n to n plus 4?
N to n plus 3.
Because
Uh,
like you are dissecting a triangle into four, so you are getting four more triangles, and like you are deleting the original one. So that's into n plus 3 actually.
no, wait, the induction idea was this. For here you do n and here you do 4.
Achha, okay, here you do n and here you do 4.
Yeah, like by dropping
Okay,
this
we can go
perpendicular.
to n plus 3 also then. Like
How,
once you have n, then you can take one triangle and you can like dissect it into four.
how do you take one triangle? Which triangle are you taking?
Like any triangle.
Okay. Instead of parallel sides, draw sides that will make isosceles triangles in the second. Like, okay, I don't know what you mean by hexagon, but that is sort of correct. Like, no, I'm not sure what you mean. Can you draw it if you're on the mirror? Or like,
Like I guess saying like similar to parallel sides, just draw such that it forms a hexagon inside the triangle and the sides connecting to the vertex
like hexagon, but
Like
where's
just
the
just mark cuts at the three corners.
yeah. Like three cuts to the triangle such that at least the vertices no, not through the vertices,
Like cut
like
the
through the
corner with the
edges.
scissor. Corner cut.
is
Yeah,
this?
like this,
Okay,
like this.
Yes. Now the middle
Such
is
that
cut.
the
okay, but
triangles at
well,
the sides.
okay, I see what he meant, but what are we doing with this? We know nothing about hexagons right now. This hexagon could be very random, like it's not a regular hexagon, certainly. What are you going to do with the hexagon? Okay, you showed this. Okay, but how do you know any of these are isosceles? How are these isosceles? How is this isosceles?
Arham, over there, like when you get a triangle into an isosceles triangle, you just pick one of the triangle and dissect it into four more isosceles triangles. So you go from n to n plus 3, right?
Over here.
No, no, like say you have a construction for n isosceles triangles, you can dissect it into n isosceles triangles.
Okay.
Now I pick one of those isosceles triangles and
Yeah.
then I dissect that isosceles triangle into further four isosceles triangles, which I can do.
Further four.
Yeah.
Okay.
So that will go from n to n plus 3.
So wait, you dissect this into n. It could be like some random n.
Yeah,
Whatever.
yeah. And then you
Now,
pick one isosceles and dissect this into four.
and now you get four more. So
Yeah.
that's n minus 1 plus 4.
So
Sure,
that
that
is
gives n plus 3 as well. That does give n plus 3. Okay. Still not what we want entirely. Okay, I'll give you a hint. Like, if you've ever proved, like, in school, if you've proved SSS congruence, like, you've probably done this before. Do any of you remember the proof?
For what? For what?
Like, you know how you prove the congruence criteria in school, right?
Yeah.
So while doing that proof, you made some sort of construction. If you remember what that construction is, that solves this
Like
problem.
radius with the like we make a line and then we imagine like two circles radius like and then we show that they connect at one side on
Okay, wait,
intersection.
I'm not sure if that was it. Um, no. Wait, okay, Shreyas really wants me to see this, but I don't see anything. Okay, you deleted it. Okay. Okay, wait. So what does non-isosceles mean? A equals B equals C is not allowed. Not allowed. So then what do you have? Like, without loss of generality, some two sides are unequal. So say A is greater than B, right? Let's say A is greater than B. So like there's some B and we know A is greater than B. What can you do now?
You can make a isosceles triangle, like just take a
Exactly.
point on the CB
So
and
you take some
connect
A
it.
prime. You take A prime so that these are equal. Now we have this. And now we have this triangle A prime B. This is still induction. Wait, Adish? Oh, yeah, this is induction. It's not geometry, don't worry. But it is geometry, but it's induction. Anyways, so we have this triangle. We got one isosceles triangle, and now we have another triangle. We know that n works. Like given any triangle, we can dissect it into into n isosceles triangles. So, well, we have one here. We have n here. We can break this into n. So we got n plus 1. That finishes. Does everyone see why?
Yes.
Okay. I guess class is over time. Do people want to continue? I can probably do like one last problem. It will go until 8. Overtime is a lie. Okay, yes, continue. Sure. Uh, there is buffer. I showed it to you before. Wait, like where did it go? Here. I'll send you the handout after the class. Like I compiled some problems. Very difficult problem for the end. Okay, let's see.
Do 2009 basic question.
2009. I don't have that. Do
Oh,
you want me to look it up?
yes.
You want to do the INMO? Are you sure? That problem still has some trauma. I prefer not to do it. Which one of these do you want to do? We can prove Euler's formula. We can do RMO though. RMO 24p6. Or we can do like a TST problem, which is actually very nice. It's from Slovenia. Please do 1.4. I'm not doing INMO. You can I'll give you all the problems, you can do them on your own. If you want to do the INMO problem, do it. Let's do Euler's formula. Okay. Uh, I will share it. I'll just send it in common room, and I guess the organizers can send it in the P sets or whatever. Yes. Okay. Does everyone know what a connected what will be uploaded? The video. I assume so, yes. Okay. For starters, does everyone know what a connected planar graph is? Okay, you don't know. That's fine. You probably wouldn't know. Okay, so do you know what a graph is at least? Okay, you know what a graph is. Okay, so a graph is some collection of points. We call them vertices, and some subset, like some collection of edges between these vertices. Okay, I should add simple for now. We will assume that vertices are, we don't have like an edge like this. So we have some edges and some vertices, and that's a graph. What's connected? Okay, say take any vertex V and take some other vertex W. Connected means there's some way to reach W from V by traversing the edges of this graph. Is that the case over here? It's not, right? Like V is not connected to anything. It has no edges. But okay, suppose we add some edge. Now is this graph connected?
No.
No, it's not.
Like, how do we like reach that? Like the
Wait, no.
line. No,
These are
wait.
the vertices which I've darkened.
Yeah, but there is no edge between them, like between these two like horizontal line and the
Huh?
like the five vertices in between and the two vertices forming the horizontal line.
Wait, let me clarify what are the vertices of this graph right now. These are the vertices.
Yeah, so like how is 2 connected to 6 is what my question is.
Okay, yeah, you're right. Okay, so it's not connected. All right. Uh, now is this connected? It's still not. Why? Three. Wait, no, is it? Not.
Yeah,
Yeah,
it's
this should be
connected now.
connected now. This is connected. Okay, so that's what connected means. You can reach any vertex from any other vertex by following the edges. How did I plot? What do you mean by that? I just drew this. Like you put the numbers randomly. Oh, no, no, no. Sorry, that I was just clarifying which were counted as vertices of this graph and which weren't. It doesn't matter. I'll erase the numbers. Okay, so we know what a connected graph is. Now we will see what a planar graph is. So a planar graph is a graph where when you draw the vertices and you draw all the edges, there is no intersections. For example, this graph is planar. Okay, this is also planar. This is also planar. This is still planar, but this is not planar. These 2 points are points of intersection, but they're not vertices of our graph. So that's not allowed. So does everyone see what a planar graph is?
So we can use curve lines, right? We can connect the both of them like
Sure,
through a
we
curve
don't
line.
care about how those lines look. This is a valid edge, and this graph is still planar. This is also valid. This graph is still planar, but now you can't connect these two in any way so that the graph remains planar. There's just no way to do it. We won't prove that, but like, come on, you can see that. All right. So for a connected planar graph with V vertices, E edges, and F faces. Okay, what is a face? A face is any like connected like it's any region inside this. So this is a face, 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 and finally the outside is also a face. So there's 6 faces in this graph. Then V minus E plus F equals 2. You've certainly seen this in school before. Okay, so we will prove this. Let's just verify this for this particular case. So what is V here? 1, 2, 3, 4, 5. Okay, 6. What's E here? 1, 2, 9. Wait, no. 8. Wait, what? Uh, 10. My bad. And F is also, we just counted 6. And so that's 2. That does hold. Okay. Now we want to induct. What should we induct on? So what do you induct on is often a very important question. Like in some problems, the main thing is to figure out what you want to induct on, right? But over here, we're given what to induct on the number of edges. So that makes stuff a lot simpler. Okay. So when you're doing induction, you need a base case. What's the base case? Well, E equals 0 can be a base case, but that's not interesting. If E equals 0, then you can't have more than 1 point, right? Because it's not connected anymore. So if E equals 0, then V equals 1 and F equals 1. So 1 plus 1 equals 2. All right. Let's look at another base case. You don't need more than one base case, but often it can help to look at more than one base case. It might give you ideas on how to work on the problem. So equals 1. Now you can have 2 points. They're connected by a line. There's still only one face, remember. Everything is the exterior. This still does not have any interior. So that's 2 minus 1 plus 1, which is equal to 2. Okay, now we're ready to induct. Suppose Euler's formula holds when E equals K. This would be the induction hypothesis. Okay. So now we want to show it for K plus 1. So we take some graph. We can induct for tree to prove. Sure. You can. Yeah, that's one of the cases in your induction. So okay. So you have some graph. It's planar, it's connected, and it's simple. So there's no weird edges from a vertex to itself. Okay. Now there's 2 cases. Case 1, your graph is a tree. What's a tree? Okay. I'm not gonna tell you all the properties of a tree right now because we don't need them. But essentially, a tree is a graph with no cycles. So, okay, wait, I should move a bit. Right. Yes. So a tree is a graph with no cycles. If it has k vertices, it has k minus 1 edges. And yes, no cycles. And since there's no cycles, there's only one face. Okay, a cycle in a graph is any. Wait, what is a cycle? Let me think. Yeah. So a cycle is if you have some vertices v1, v2 till say vm, and there's an edge between v1 and v2. There's an edge between v2 and v3. There's an edge between v something and v something plus 1. And then there's an edge between vm plus and v1. So, for example, this is a cycle. And this is a cycle. So a tree has no cycles. Okay, so what happens when there's no cycles? There's only one face. That's the exterior. The graph doesn't really have an interior. So f equals 1. And this is a property of trees, but E is equal to k plus 1. So wait, no. We're doing induction on the case of k plus 1. So suppose equals k plus 1. Then in a tree, the property is that there's always one more vertex than edges. So v equals k plus 2. And you can verify that Euler's formula holds here. That's not very interesting. So we will look at the other case, which is a graph has some cycle. G has a cycle. Okay. So we have some graph. And it has some cycle. It's still planar, but it has some cycle. Okay. So we want to induct. We have k plus 1 edges, and we want to get k edges. How do we go from k plus 1 to k? Does anyone have ideas? This is our graph. Okay. So take some edge which is part of a cycle. So there's some edge E. It belongs to a cycle. It could be like this edge as well. It could be any edge which is part of a cycle. We will delete that edge. So now we have k edges. Wait, but like let's go back a bit. What happened when we deleted that edge? There's okay, wait, let's look at a slightly different graph. Okay, let's look at this. So what happens when we deleted that edge? Well, originally, this was a face and this was a face. Now we deleted that. So we deleted a face as well. So V is the same. E is now K, and F reduced by 1. It reduced by 1. So in this new graph, this has how many edges? It has k edges. So what can we do with a k edge graph? We can use that induction hypothesis. So V minus k plus F minus 1 equals 2. So do some algebra, and V minus k plus 1 plus F also equals 2. And this is just our original graph, right? This is the number of edges in our original graph. This is the number of faces in our original graph. So we are done. That verifies Euler's formula. And by induction, we are done. So this will hold for all k. Any questions? All right. I think this is a good place to stop. So I will stop the recording.